Hi everyone. In this video, we're going to continue working on, let's see if I can find our picture, the problem from the beginning of packet 1.1. So we have gone through and calculated an average rate of change for this position function and figured out that it was an average velocity. And now I want to crunch through a few more of these average velocities and start to talk about a little bit of a pattern that we're seeing here. So let's see. There's the picture I want. Okay, so I'm not going to crunch through all of these. Oh, and notice that I had them not quite in the order I was really wanting them. Over here, they were in the wrong order, these three, so it should be 0.81 and 1.2 should be switched. Okay, so I'll show you kind of a nice quick, well, sort of quick, a nice convenient calculator way to get some of this info, especially if you need to do quite a few of these calculations. So I'm going to go into my y equals and I'm going to enter the equation that we've been working on. So it was this 64 minus 16 times t minus 1 squared. So I'm going to put that in my y equals, and if you remember, we actually had a really nice window here, so I'm just going to duplicate that. So I'm going to hit the window button right below the graph screen, second one over, and I'm going to, I actually think I've already been playing around with this, so it might be just right. I want my x-min to be 0 and my x-max to be 3, just as in the graph I started with, so you can see I've got that 0, 3. And then the scale, x scale, is just how far apart your tick marks are. So if you really wanted to match, they were 0.5 apart before, and that's what I've copied. And then I want my y's to go from 0 to 64, but I'm actually bumping them up just a little bit because when a point is right at the top of your screen, sometimes it's a little hard to read cursors and stuff. So giving myself a tiny bit of extra room, and then the tick marks were 4 here, so I've made them 4 here. Okay, so once you've done that, you can hit graph. And then back to my table, I want to calculate, for starters, the average velocity from 0.4 to 0.8. So we can do some of that plugging in on the calculator. I'm going to hit the trace button right next to the graph button, and then you can just type in a value. So if I want to know s of 0.4, I'll just type in 0.4 and it'll find my y value for me. So it looks like it was 58.24. So we're going to take 58.24 and we're going to subtract it from s of 0.8, which is 63.36. And then we're going to divide that by 0.8 minus 0.4, which is 0.4. So we get 63.36 minus 58.24 divided by 0.4, which is a 12.8. And all of these are very similar, so if you want a little bit of calculator practice, feel free to crunch through some more and see what's going on. But I'm just going to fill in. I've done these ahead of time. So this is 8 feet per second, and this one was 6.56 feet per second, and this one was 6.24. Again, notice that I did change the order here. The idea was to make these intervals shorter and shorter near the interval or the endpoint 0.8, so I had them in the wrong order. This one was 4.8, and this one actually ends up being 0. And we can look at the picture just to see what's going on. I'm just hiding it from myself. Okay, so we did intervals. 0.8 was part of all of these intervals, and we let the other endpoint move around. So we did one from 0.4 to 0.8. So there was a secant line, and then we did 0.7 to 0.8, so we moved that point a lot closer, and there's just a little bit shallower tangent line, and then we did 0.79 to 0.8 really close together, and then on the other side we did 0.81, so just slightly on this side, and then 0.9 a little bit further on this side, and then we went all the way out to 1.2, and what's happening here is we've got some symmetry. We're the same distance from the vertex, so that's why we're getting an average rate of change of 0, because, well, we know that the ball went a little higher and then came back down. The only information that average velocity calculation is getting is that we started at a certain height and we ended up at that exact same height, so it's thinking we didn't do anything at all, and that's where average velocity is not perfect. It can fail us a little sometimes. Okay, so going back to this, what I'd really like to do is kind of boil this down to a discussion of if I want to talk about how fast the ball is going right at 0.8 seconds, what I'd really like to see is as this interval gets shorter and shorter and shorter, the slopes of these secant lines are starting to get pretty close to what looks like is my tangent line. So we're seeing this connection between slopes and average velocities, and that's going to lead to a connection between slopes of secants and average velocities. That'll lead to a connection between slopes of tangent lines and instantaneous velocities. Okay, so just a little bit more calculator work in this one. I'm going to go back to that graph, and what I'd like to do now is zoom in on that point 0.8, 63.36. So I'm going to trace, I'm going to go back to that point, and I'm going to hit the zoom button. Let me move up just a little so you can see what I'm doing. Zoom, and then I'm just going to zoom in right on that point, and it messes with it a little bit, but close enough. Okay, so there I'm zoomed a little bit. I was trying to get 0.8, 63.36. I think that's a little closer. And so you can recenter every time, but just hitting enter again will make it zoom again. You don't have to go back into the menu. 0.8, 63.36. I think that's still my closest. That's actually looking pretty good. Okay, so what I hope you see as I zoom in and zoom in and zoom in is that at this point that really looks like a straight line, and it should. And this is the whole idea. If you want to talk about the slope of a tangent line or the instantaneous velocity, what you're talking about is if you zoom in far enough on a nice smooth continuous function, it will look like a straight line. And if you can find the slope of that straight line that it looks awfully close to, then you've got an instantaneous rate of change. And that's a really cool thing. So that's what we're working on. Okay, so graph appears. Okay, so we figured out that this is starting to look an awful lot like a straight line. And we want to now use a few different methods to try and estimate the slope of that tangent line that we're looking for. So we saw it looks like a straight line. We'd like to approximate the slope. One way to do this is numerically. So it's looking at what we did here. When we went 0.4, I'm sorry, not 0.4. Yeah, 0.4. Yeah, 0.4 in either direction. We got slopes of 12.8 and 0. When we got a little closer, it went down to 8 on this side and up to 4.8 on this side. When we went even closer, we have these really tiny intervals, 0.79 to 0.8 and 0.8 to 0.81, and one gives us a slope of 6.56 and one gives us a slope of 6.24. So one way to estimate the instantaneous velocity would be numerically plug in some numbers and try and kind of look for a trend. And if it looks like there is a trend, you could do something like just averaging this. So this is numerically. We would take 6.56 plus 6.24 and we would divide it by 2. So just average slopes of secant lines. And you want to pick pretty short intervals if you're going to do this, and it's nice to always make an interval that goes to the left and an interval that goes to the right. Or you could even say, if I'm interested at what's happening right at 0.8, I'm going to pick the interval from 0.79 to 0.81, and 0.8 doesn't actually have to be in your interval. Okay, so I was going to calculate that. 6.56 plus 6.24, whoops, over 2. And that gives me 6.4. And in general, this is just going to be an estimate, what we just did, but it's not a bad estimate. We know it's somewhere between 6.56 and 6.24, so we're just going to guess right in the middle. Another way to do this is to just ask your calculator to straight up tell you. So you need a calculator that can figure out a derivative numerically. Meaning it'll just tell you the derivative at a point, and this one will do it. So I'll show you this. This is getting a little ahead. We haven't even named the derivative yet, but that's really what we're doing. So numerical derivative, oh, I'm kind of speeding through here. What I've done is I hit the math button, And then under the number menu, if you just work your way down, you should see numerical derivative, and then you just type in your function. So really important that you put your variable, whatever your variable is, put it down there. So I don't know why it asked, because it generally makes us use x. But we're using x, and this was 64 minus 16 times x minus 1 squared. And then we're supposed to give the x value, which is 0.8. So the calculator will tell us, and actually we got really kind of lucky here. So this is n deriv on the calculator. And it told us that it was 6.4. And the reason we're actually getting lucky is because this is quadratic. Some kind of nice things happen when you're working with quadratics. And then I have one last option for you. So last option, you should be able to figure this out on your calculator one way or another. There is another, is graphically we could go in here, and I'm going to go back to my original window, 0 to 3 and 0 to 68. And if I can remember where to find it, calculate, there it is. Okay, so once again, we're getting a little ahead of ourselves, but this dy dx is a derivative, slope of a tangent line. And you can snag that, and you can plug in the 0.8, and there it is again. It tells you down at the bottom, if you can see that the slope is 6.4. You can even, while we're on the calculator, get it to draw. Let me make sure I remember how. You can get it to draw a tangent line. Maybe I'll do that in a different video though, because it's slightly involved, but that is the thing, or you can look it up if you like. Okay, so anyways, you should be able to get an estimate for the slope of a tangent line, and you should also be able to get your calculator to give you the approximate slope of a tangent line. Those are two things that you'll want to be able to do. All right, let's see. Next, we are supposed to estimate the instantaneous velocity of the ball at t equals 1.2, and then see how the sign is telling us something about the behavior of the ball. So I'm going to go ahead and use the graph one again because I kind of like it. So here's the graph, and I am going to calculate dy dx. So this is slope of a tangent line, whenever you see that. And I want to know what's happening now at 1.2. So if I plug that in, I get negative 6.4. So at 1.2, I'm getting a velocity of negative 6.4. And we actually looked at this before. Remember, what was interesting is here at 0.8, we have some symmetry with over here at 1.2. And so what we're getting is very similar tangent lines, but one has positive slope and one has a negative slope. So what the negative is telling me, ooh, not meant blurry focus, please come back in. Maybe. There we go. Okay, sorry. Turn that autofocus off. What we're getting here is this negative slope. It's telling us that the height of the ball is decreasing by 6.4 feet per second. So basically, a positive velocity tells you that you're getting further away from your starting point, and a negative velocity tells you that you're getting closer to your starting point. That's one way to look at it. In this case, it's up and down. Positive velocity is up, negative velocity is down. So there's a direction associated with velocity, and that's what the positive or negative will tell us. Okay, last one here. Without using our calculator or doing any calculations, what do we expect the instantaneous velocity to be when t equals 1? And that's right at the vertex. So if we were to draw in that tangent line, remember the slope of the tangent line is the instantaneous velocity. That looks like a horizontal line. So it looks like my instantaneous velocity is 0 feet per second. And I think that should make sense because we have the ball headed up, 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 and then it hits the top, and it has to come to a stop for at least an instant before it heads back down. So that's what we've just found.